Hello and welcome to lesson number 22, integration part 2. If you haven't seen the first part, click this video in the top right here. So then, starting off lesson number 22, let us find the integral of 1 divided by the square root of a squared minus x squared with respect to x. We're going to find this for a being a positive number, and it's going to be valid for x's that are between negative a and a, as in x less than a and x greater than negative a. For these conditions, let's find the integral of this thing right here. In order to do this, we're actually going to be finding it by trying to find the derivative of the answer and showing that that derivative is in fact equal to this. This is the same strategy that we used previously for other things. We're going to be using it here as well. So then, this is actually equal to the sine inverse of x divided by a. In order to show that, we're going to start with the sine inverse of x divided by a and go backwards. So we'll start with y equals the sine inverse of x divided by a and try to go backward to find that its derivative is equal to 1 divided by the square root of a squared minus x squared, and thus that in fact the integral of 1 divided by the square root of a squared minus x squared is in fact equal to the sine inverse of x divided by a plus c. Starting from here, what we're going to do is take the sine of both sides. Taking the sine of both sides, we can see that the sine of y is equal to the sine of the sine inverse of x divided by a, which is going to be x divided by a. Now, taking all of this such that x is the subject, we can have that x is equal to a times the sine of y. Now, let's take the derivative with respect to y. So then we have to take the derivative of x with respect to y on the left, which is going to be equal to the derivative of a times the sine of y with respect to y on the right side. A is a constant, so we can take it out, so it's just a times the derivative of sine of y with respect to y. The derivative of sine of y with respect to y is going to be the cosine of y. So therefore, dx by dy is a times the cosine of y. From our rules, we know that dy by dx is going to be 1 divided by a times the cosine of y. Now what we're going to do is use the identity that the sine squared of x plus cosine squared of x is equal to 1 for any x elements of real numbers. If you want to know more about that, click this video on the top right here. So then, applying that to this situation, we have that the cosine squared of y, cosine squared y would be equal to 1 minus the sine squared of y, which would be equal to 1 minus, and sine y is equal to x divided by a, so sine squared y is going to be equal to x squared divided by a squared. Taking this under a common denominator of a squared, we can write this as a squared minus x squared divided by a squared. Therefore, the cosine of y would be the square root of this thing. Cutting that and substituting, we can see that dy by dx would be equal to 1 divided by a times the square root of a squared minus x squared divided by a squared. Now here, since a is a positive value, a squared square root is actually just a. So we can take that out and say that this is going to be equal to 1 divided by a times the square root of a, 1 divided by a squared, which is going to be 1 divided by a times the square root of a squared minus x squared. Now then, since we have this, you can see this a and this 1 divided by a cancel, leaving us with just the square root of a squared minus x squared. Therefore, from this we get that dy by dx is equal to 1 divided by the square root of a squared minus x squared. Dy by dx is in fact the derivative of the sine inverse of x divided by a. Therefore, we could say that the derivative of the sine inverse of x divided by a taken with respect to x is equal to 1 divided by the square root of a squared minus x squared. Now then, we know that if one function is the derivative of another function, then we can invert this process and say that the second function's integral is going to be the first function, plus of course a constant. So therefore, from this we can say that the integral of 1 divided by the square root of a squared minus x squared dx for the valid conditions above, as in a being a positive number and x being in between negative a and a, given these conditions, then the integral of 1 divided by the square root of a squared minus x squared is going to be equal to this function on the inside, which is the sine inverse of x divided by a plus a constant c. an arbitrary constant c. We don't know what it is. It is a set of constants that could be there. We are representing every single possible constant with a single value c. Moving on, we're going to do a similar thing to this proof for 1 divided by a squared plus x squared. For this thing, we're going to write the integral of 1 divided by a squared plus x squared dx, and the only condition here is that we're going to have a being not equal to 0, so I'm going to write just that a greater than 0, because a could be less than 0 as well, but then all we have here is just a squared. So whether a is less than 0 or greater than 0, a squared is going to be greater than 0. So it really makes no sense to need an a being negative, so we just put a being positive. For this, what we're going to do is once again take the answer and rearrange it backwards by taking its derivative and try to find that the derivative of our answer is equal to 1 divided by a squared plus x squared. In order to do this, let's start with the tan inverse of x divided by a. Let's consider y is equal to the tan inverse of x divided by a. Taking the tangent of both sides, we can see that the tangent of y would then be equal to x divided by a, i.e. taking x as the subject, x would be equal to a times the tangent of y. Now let's take the derivative of both sides with respect to y. On the left side, we get dx by dy being equal to, a is a constant here, so we leave it, and the tangent of y's derivative with respect to y is going to be secant squared of y. From our identity sin squared plus cosine squared of any angle is equal to 1, we can derive that 1 plus the tangent squared of any angle is equal to secant squared of that angle. So we have 1 plus tan squared of y equal to secant squared of y. Therefore, from this, we can substitute this expression into here and write that dx by dy is equal to a times 1 plus the tangent squared of y. Next, let's substitute tan y as being x divided by a. So then we have dx by dy being equal to a times 1 plus tan squared y is going to be x squared divided by a squared. Taking common denominator of a squared, we have to multiply this 1 by a squared, leaving us with a times a squared plus x squared divided by a squared. Now then, cancelling out one of these a's in the a squared with this a, we are left with a squared plus x squared divided by a. If dx by dy is a squared plus x squared divided by a, then dy by dx would be a divided by a squared plus x squared. Now then, here we can see that the derivative of tan inverse of x divided by a with respect to x is equal to a divided by a squared plus x squared. From this, we can reverse this and say that the integral of a divided by a squared plus x squared with respect to x is going to be equal to the tan inverse of x divided by a plus c. Usually, however, this is not the format that we write this in. Usually we take this a to the other side. Dividing both sides by a, we can see since a is a constant, there's no problem with this. We get on the left, when we divide this thing by a, we get 1 divided by a squared plus x squared integrated with respect to x. And on the right side, dividing both sides by a, we get 1 divided by a times the tan inverse of x divided by a plus c divided by a, which is just another constant, so we'll just rewrite it as c. Therefore, the integral of 1 divided by a squared plus x squared dx is equal to 1 divided by a times the tan inverse of x divided by a, provided that a is greater than 0. If a is equal to 0, we can see within this thing and within this thing we have divided by zeros, which we want to avoid. So then, avoiding those cases, the integral of 1 divided by a squared plus x squared with respect to x is equal to 1 divided by a times the tan inverse of x divided by a plus c. Let's look at some quick examples of applications of these before we move forward. So then, let's consider first this integral here. We'll call it I. I is the integral of 1 divided by the square root of 4 minus x squared with respect to x. Here we can see this is also the integral of 1 divided by, we can rewrite 4 as 2 squared. So then we have 2 squared minus x squared. Now what we're going to do is use the formula that we had above. We know that when we have the pattern of 1 divided by the square root of something squared a squared minus x squared, then that integral is going to be the sine inverse of x divided by a plus c. Therefore, in this particular case, since we have the integral of 1 divided by the square root of 2 squared minus x squared, it is going to be equal to the sine inverse of x divided by 2 plus c. Hence, we have our answer. Similarly, let's consider the second option. This one is using tan inverse. Let's call this integral I. I is the integral of 1 divided by 3 plus x squared. We should notice that when we have this, we could write 3 as being equal to the square root of 3 squared. So we have the square root of 3 squared plus x squared dx. And now we have a pattern that we know. We know that when we have 1 divided by a squared plus x squared's integral, it is equal to 1 divided by a times the tan inverse of x divided by a plus c. In this case, from our pattern, a is equal to the square root of 3. Therefore, our answer for this is going to be 1 divided by the square root of 3 times the tan inverse of x divided by the square root of 3 plus c. So therefore, here for this thing, our answer is going to be equal to 1 divided by the square root of 3 times the tan inverse of x divided by the square root of 3 plus a constant c. Hence, we have our answer. So these are just some examples of the kind of question you will need to solve using these methods. Usually in the exam, of course, your question that you need to solve, the integral that you're looking for, it does not only contain this bit, it has other components which you can then split into separate integrals, and some of those integrals will give you equations of this form, which you can then simplify into either tan inverses or sine inverses depending on the application. The next thing we're going to be considering is the integral of the derivative of a function divided by that function. You can see here I've written f prime x in the Lagrange notation to show you the derivative of a function f of x. So here what we have is the integral of a function's derivative divided by the original function. This is in fact equal to the logarithm of the absolute value of the function plus the constant c. In order to show that this is true, what we're going to do is instead take this answer, take its derivative, and show that when we take the derivative of the natural logarithm of the absolute value of a function f of x, we are going to get f prime x divided by f of x. So let's begin. In order to show this, we are going to start with the derivative of the natural logarithm of the absolute value of f of x taken with respect to x. So with respect to x, we cannot take the derivative of the logarithm of the absolute value of f of x directly with respect to x. So instead what we need to do is use the chain rule and write this as the derivative of the natural logarithm of the absolute value of f of x taken first with respect to f of x and then multiplied by the derivative of f of x taken with respect to x. If you don't remember the chain rule, check this video in the top right here. Moving on, if we consider the first statement, the derivative of the logarithms of the absolute value of anything with respect to that same thing, in this case f of x and f of x, is going to be 1 divided by that thing. So if we have the derivative of the natural logarithm of the absolute value of f of x taken with respect to f of x, then that derivative is going to be 1 divided by f of x. As for the second thing, the derivative of f of x taken with respect to x in the Lagrange notation is written as f prime x. So therefore what we have is our answer of f prime x divided by fx. Therefore, when we take the derivative of the logarithm of the absolute value of f of x with respect to x, we get f prime x divided by fx. Therefore, reversing the process, if we consider the integral of f prime x divided by f of x with respect to x, this is going to be the logarithm of the absolute value of f of x plus the constant c. We are going to be using this identity in order to find the integrals of tan x, cotangent x, secant x and cosecant x. Previously, with our basic rules, we were only able to find the integral of sin x and cosine x, but now with this rule, we can find the integrals of the other 4 trigonometric functions. So let's go. Starting off with the tangent of x. Consider the integral of the tangent of x with respect to x. We know that the tangent of x is equal to the sine of x divided by the cosine of x. Therefore, we can write this as being equal to the integral of the sine of x divided by the cosine of x with respect to x. Now then, consider the derivative of the denominator. The derivative of the cosine of x with respect to x, as we found earlier, is equal to the negative sine of x. Therefore, if we had a negative sine of x on the numerator here, we would have the pattern that we need of the function's derivative on top and the function on the bottom. In order to get this, let's just multiply this thing inside the integral by -1 twice. What I mean is, let's add two -1's on the inside here as such. Let's add in the integral of negative sin² divided by cosine of x dx. Since we multiplied by -1 twice, it's the same thing as doing nothing, so there's nothing wrong here. But now, we're going to take one of these negatives to the outside of the integral because it's a constant. So here we can take the negative integral of negative sin² divided by cosine x with respect to x. Now we have on top negative sin² and on the bottom we have the cosine of x. Therefore on top we have the derivative of the thing that we have on the bottom. Given this pattern, we know from our identity up above, this is going to be equal to the natural logarithm of the absolute value of the denominator function. Therefore what we have here is this negative multiplied by this integral's value, which is going to be the natural logarithm of the absolute value of the denominator function or cosine of x. So here we have negative natural logarithm of the absolute value of cosine of x plus the integration constant c. Some people take this negative to the inside because we know that the negative logarithm of a is equal to the logarithm of 1 divided by a. So you might write this as the natural logarithm of the absolute value of 1 divided by the cosine of x, or simply natural logarithm of the secant of x. I, however, don't like writing like this. I prefer to write the integral of tangent of x as the negative natural logarithm of the absolute value of cosine of x plus c. Why? Because it matches with the next integral that we're going to find, which is the integral of the cotangent of x. We're going to be using a similar method for the integral of the cotangent of x. Considering the integral of the cotangent of x with respect to x, since we know that the cotangent is equal to the cosine of x divided by the sine of x, we can write that down and say this is equal to cos² divided by sin² integrated with respect to x. Since we know that the derivative of sin² with respect to x is equal to the cosine of x, over here we already have the form of a function's derivative divided by the original function. If the original function is sin of x, then cosine of x is the derivative of sin of x. Therefore we have the derivative of sin of x divided by sin of x. Therefore this integral is going to be equal to the natural logarithm of the absolute value of the denominator function, so the absolute value of sin² and plus c. Here we can see the similarity. For the tangent of x, its integral is negative natural logarithm of the absolute value of cosine of x plus c, and for cotangent of x, or 1 divided by the tangent of x, it is simply the natural logarithm of the absolute value of sine of x plus c. Now then, let's move on from these two into the secant of x and cosecant of x. For these two, we actually use a little bit of a trick, and I'll show you that trick right now. Consider the integral of the secant of x with respect to x. What we're going to do here is to multiply the numerator and the denominator by secant of x plus tangent of x. So basically what I'm going to do here is write that this is equal to the integral of the secant of x multiplied by the secant of x plus the tangent of x, and then again divide by the secant of x plus the tangent of x. Now here, since we are multiplying and dividing by the same exact thing, it's the same as multiplying by 1, so there's nothing wrong here. However, when we do this, we can see this secant of x multiplies with this thing to give us secant² of x, and secant of x times tangent of x gives us sec² tan x. So here we have the integral of secant² of x plus secant of x times the tangent of x divided by secant of x plus tangent of x. Now here I want you to observe the fact that from earlier we found, from the previous video which you haven't watched, click this video in the top left, top right over here, the derivative of the tangent of x with respect to x is equal to the secant² of x, and the derivative of the secant of x with respect to x is equal to the secant of x times the tangent of x. Using this, if we look at the numerator and denominator, we can see the derivative of secant of x is secant of x tangent of x, and the derivative of tangent of x is secant² of x. Therefore, if we take the derivative of the thing on the bottom, we do in fact get the thing on top. Therefore, what we have here on top is the derivative of the secant of x plus the tangent of x. So we essentially have the integral of the derivative of secant of x plus tangent of x divided by secant of x plus tangent of x, which is exactly the same as the form that we had above. Therefore, this integral is going to be equal to the natural logarithm of the absolute value of the denominator function, which is secant of x plus the tangent of x. Therefore, we have that the integral of the secant of x with respect to x is equal to the natural logarithm of the absolute value of secant of x plus tangent of x. We can do a similar thing for the cosecant of x, somewhat unsurprisingly. If we consider the integral of the cosecant of x with respect to x, we once again have to multiply the top and the bottom by the same value, except this time we're going to be multiplying the top and the bottom by the value cosecant of x minus cotangent of x. So what we're going to do is multiply the cosecant of x by cosecant of x minus the cotangent of x divided by the cosecant of x minus the cotangent of x. Once again, since we're multiplying the top and bottom by the same thing, as in we're multiplying and dividing by the same value, it's the same exact thing as just multiplying by 1. So there's nothing wrong here. Continuing, however, we can see that if we multiply the cosecant of x to the top bit here, we have the integral of cosecant squared x minus cosecant x, cosecant x times the cotangent of x divided by cosecant of x minus the cotangent of x. Unsurprisingly, the thing on top is actually the derivative of the thing on the denominator. We can see this if we individually take the derivative of cosecant of x and the negative cotangent of x. We know that the derivative of the cosecant of x with respect to x is equal to the negative cosecant of x times the cotangent of x. We also know that the derivative of the cotangent of x with respect to x is equal to the negative cosecant squared of x. From this we can say that the derivative of the negative cotangent of x would be equal to the positive cosecant squared of x. Therefore, the derivative of the negative cotangent of x is cosecant squared of x, and the derivative of cosecant of x is negative cosecant cotangent of x. From this we can see that the thing on top really is the derivative of the thing on the bottom. So here what we have is the derivative of cosecant of x minus cotangent of x divided by cosecant of x minus cotangent of x. Therefore, the integral of cosecant of x is going to be equal to the natural logarithm of the absolute value of the denominator, which is cosecant of x minus the cotangent of x plus c. Therefore, we have the integral of the cosecant of x. With this, we have now shown the integral of the tangent of x, the integral of the cotangent of x, the integral of the secant of x, and the integral of the cosecant of x. Using this new knowledge, we can now solve integrals that we couldn't solve previously. An example integral is given here. This integral is trying to find the area under the curve of tangent of x from x equals 0 up to x equals pi by 4. So then, using our previous knowledge of the indefinite integral of the tangent of x, which we know from above, is equal to the negative natural logarithm of the absolute value of cosine of x plus c, we know that if we have the definite integral from 0 to pi by 4 of tangent of x, it must be equal to the application of the limits of natural logarithm of the absolute value of cosine of x from 0 up to pi by 4. Therefore, the value of this integral is going to be what happens when you substitute pi by 4's limit minus what happens when you substitute 0's limit. When you substitute pi by 4's limit, you get negative natural logarithm of the absolute value of the cosine of pi by 4 minus the lower limit, which is the negative natural logarithm of the absolute value of the cosine of 0. Now then, taking this thing, on the left, the cosine of pi by 4 is equal to 1 divided by the square root of 2. The absolute value of 1 divided by the square root of 2 is equal to 1 divided by the square root of 2, since it is a positive value. Therefore, on the left, what we have here is the negative logarithm of 1 divided by the square root of 2. And then this minus and this minus will cancel to give us a plus. So what we have is a plus natural logarithm of the cosine of 0 is going to be 1, and the absolute value of 1 is going to be 1. So what we have here is simply the natural logarithm of 1. Now then, going downward, we know that 1 divided by any value is that value to the power of negative 1. Therefore, 1 divided by the square root of 2 is the square root of 2 to the power of negative 1. So, square root of 2 to the power of negative 1. We also know that the root of any value is going to be that value to the power of a half. Combining these two, we know that the 1 divided by the square root of 2 is equal to the square root of 2 to the power of negative 1, which is equal to 2 to the power of negative 1 half. Therefore, we can replace 1 divided by the square root of 2 with 2 to the power of negative 1 half. Another thing we know is the natural logarithm of, for a matter of fact, any logarithm of 1 is equal to 0, because any value to the power of 0 is equal to 1, except for, of course, 0. 0 to the power of 0 has problems. We are not going to discuss that one. But any other value to the power of 0 is going to be equal to 1. Therefore, the logarithm, any base of 1 is going to be equal to 0. Substituting those two in, we have negative natural logarithm of 2 to the negative 1 half plus 0, which we can cancel. Now then, here we have 2 to the power of negative 1 half's logarithm. We know that when we have a logarithm, we can take the exponent to the front. Taking this exponent to the front, we can see we have negative 1 times negative 1 half, which is going to be positive 1 half. So here what we have is positive 1 half. And here we have the natural logarithm of 2, which we're going to leave alone as the natural logarithm of 2. This 0 cancels, so it's gone, which means our final answer is going to be 1 half of the natural logarithm of 2. Therefore, the integral from 0 to pi by 4 of tangent of x dx is going to be equal to half of the natural logarithm of 2. Before we continue solving more integrals, we are going to need to prove a special rule that's going to come in handy for the next few integrals. And that rule is going to be how to find the integral of f of k times some function x with respect to x. So f of k, where k is some constant, times x. Provided that we know that the integral of f of x on its own with respect to x is equal to capital F of x. So what I'm going to show you is the answer right now. The answer is that the integral of simple f of kx is going to be equal to capital F of kx divided by k. In order to show this, we are going to consider the derivative of capital F of kx. So then, let's go. Considering the derivative of capital F of kx with respect to x, we know from the chain rule that this is going to be equal to the derivative of capital F of kx with respect to kx, as in d kx, times the derivative of kx with respect to x. On the right side, the derivative of f of kx with respect to kx is going to be simple f of kx. As for this bit, the derivative of constant times x with respect to x is just going to be the constant, so times k. Therefore, the derivative of capital F of kx with respect to x is going to be simple f of kx times k. Reversing this in the integral format, we know that the integral of k times f of kx with respect to x would be capital F of kx plus c. Therefore, since k is a constant, we can divide both sides by k and write finally that the integral of f of kx with respect to x is going to be capital F of kx divided by k plus c. This is going to be quite handy in the next few integrals that we're going to solve, because those integrals contain common functions that we know the integrals of, but their inputs are themselves some constant times a function. This rule is going to make it easy for us to find those integrals, as in something like this. Let's say we want to find the integral of the sine of 2x with respect to x. Something like this can easily be found by simplifying the integral of the sine of x, which is the negative cosine of x. So here, in this case, we need to substitute the negative cosine of 2 times x, as in negative cosine of 2x, divide by that k, which is 2, so divide by 2. We are going to be quickly using things like this, which is why I needed to prove this rule quickly. So now let's go on to finding some integrals that are going to use this rule, starting off with the integral of sin² of x. The integral of sin² of x is going to be found by using an identity of the cosine of 2x. We know that the cosine of 2x is equal to the cosine squared of x minus the sine squared of x. We also know that the sine squared of any angle x plus the cosine squared of that angle x is equal to 1. Using these two identities, we can derive another two forms of the cosine of 2x. For the first one, let's consider this equation and take the cosine squared of x to one side. Therefore, the sin² of x is equal to 1 minus the cosine² of x. Taking the negative value of this, we can see that the negative sin² of x is equal to -1 plus the cosine² of x. We are going to be substituting this thing in for this negative sin² of x in order to find the cosine of 2x in a different format. Doing so, we can see we get cosine² of x, and then this minus sin² of x turns into -1 plus another cosine² of x. The two cosine² of x's add together to give us 2 cosine² of x, and then this -1 stays as -1. So therefore, this is another form of the cosine of 2x. We can write it as 2 times the cosine² of x minus 1. Another form of this is to take the same equation, except this time we are going to swap the sine and the cosine, and we are going to write the cosine² of x being equal to 1 minus the sin² of x. This is coming directly from this middle equation here. Using this, we're going to be substituting that into this above thing. So when we do that, we can see the cosine² of x becomes 1 minus the sin² of x. This negative sin² of x and this negative sin² of x become 2 sin² of x. So here what we have is 1 minus 2 times the sin² of x. These are three different forms of the cosine of 2x. For our purposes, we're going to be using this form and this form in order to get expressions of the sin² of x. Erasing some of this little crosswork that we have here, writing the identity in the top right, we can see from this identity that 1 minus 2 times the sin² of x is equal to the cosine of 2x. Therefore, 2 times the sin² of x is going to be equal to 1 minus the cosine of 2x. Therefore, the sin² of x is equivalent to 1 minus the cosine of 2x divided by 2. Therefore, in this integral, we could replace the sin² of x with 1 minus the cosine of 2x divided by 2, which is exactly what we're going to do. We would replace with 1 minus the cosine of 2x over 2 dx. Now then what we're going to do is take this 2 to the outside as 1/2, because it's a constant, we can take it out of the integral as we please. Then we have 1/2 times the integral of 1 minus cosine of 2x, which we can again split as the integral of 1 with respect to x minus 1/2 times the integral of the cosine of 2x with respect to x. For the first bit, the integral of 1 with respect to x is simply x. So then multiplying that by the half, from this bit we get x divided by 2. As for the second bit, we get a -1/2 on the outside, so -1/2, and then this integral here is the integral of the cosine of 2x, which is going to be, according to our rule, the integral of cosine x substituted with 2x divided by the constant 2. The integral of cosine of x is going to be sine of x, and since we have the cosine of 2x here, it's going to be sine of 2x divided by the constant, which is 2. Simplifying this down, we can see that this 1/2 and this half here could be turned into 1 divided by 4. Therefore, we can rewrite this as x divided by 2 minus sine 2x divided by 4 plus c. Therefore, this is the integral of the sin² of x. The integral of sin² of x with respect to x is going to be equal to x divided by 2 minus the sine of 2x divided by 4 plus c. Let's now go on to try and find the integral of the cosine² of x. The integral of the cosine² of x can be found with a similar method to how we found the integral of the sin² of x, by simply using our identity from above. From above, we know that the cosine of 2x is equal to 2 times the cosine² of x minus 1. Rearranging, we can see that 2 times the cosine² of x is going to be 1 plus the cosine of 2x. Therefore, the cosine² of x is going to be equal to 1 plus the cosine of 2x divided by 2. Substituting that in, we can see the integral of cosine² of x with respect to x is going to be equal to the integral of 1 plus the cosine of 2x divided by 2 with respect to x. Once again, we're going to take this 2 out as a constant, and we're going to split this integral into two pieces as integral of 1 dx plus the integral of cosine 2x with respect to x, which means we're going to have half times the integral of 1 dx plus half times the integral of the cosine of 2x with respect to x. For the first bit, the integral of 1 is x, so therefore we get x divided by 2. For the second bit, we have plus half times the integral of cosine of 2x, which is going to be the sine of 2x divided by 2, and then plus c. Simplifying out a little bit, we get that the integral of the cosine squared of x with respect to x is going to be equal to x divided by 2 plus the sine of 2x over 4 plus c. There's our answer. Next, let's find the integral of the tangent squared of x and the cotangent squared of x. Taking the tangent squared of x, we'll write the integral of the tangent squared of x with respect to x. To simplify this one, we're going to be using another trigonometric identity. From the identity sine squared plus cosine squared of x equal to 1, we can divide both sides by sine squared or cosine squared to get two different identities. From dividing by cosine squared, we get that the tangent squared of x plus 1 is equal to the secant squared of x. Therefore, the tangent squared of x is equal to the secant squared of x minus 1. We are going to be using this in order to find the integral of the tangent squared of x. Substituting in for tangent squared of x, secant squared of x minus 1, we can see this is equal to the integral of the secant squared of x minus 1 with respect to x. Here we can see, since we have a plus or minus in the middle, we can separate this into two separate integrals. The first integral is going to be the integral of the secant squared of x with respect to x, and the second integral is going to be the negative integral of 1 with respect to x. For the first bit, we know that the derivative of the tangent of x is equal to the secant squared of x. Therefore, the integral of secant squared of x is equal to the tangent of x. So for that bit, we can substitute the tangent of x. For the next bit, we have the negative integral of 1 with respect to x, which is going to be negative x. And then we have to add the constant of integration. Therefore, the integral of the tangent squared of x with respect to x is equal to tangent of x minus x plus c. Similarly, for the cotangent of x, we have another identity. For the integral of the cotangent squared of x, we can use the identity that we get when we divide sine squared of x plus cosine squared of x equal to 1 both sides by the sine squared of x. Doing so, we get 1 plus the cotangent squared of x being equal to the cosecant squared of x. Therefore, the cotangent squared of x, cot²x, is equal to the cosecant squared of x minus 1. Replacing that into here, we can see that the integral of cotangent squared of x with respect to x is equal to the integral of cosecant squared of x minus 1 with respect to x, which we can then break into two integrals. The first is going to be the integral of the cosecant squared of x with respect to x, and the second is going to be the negative integral of 1 with respect to x. For the first bit, we know that the derivative of the cotangent of x is negative cosecant squared of x. Therefore, the derivative of negative cotangent of x is equal to cosecant squared of x. From that, we can say that the integral of cosecant squared of x is equal to the negative cotangent of x. As for the next part, the integral of negative 1 with respect to x, or negative the integral of 1 with respect to x, is going to be negative x, and then of course we have to add the constant of integration. Therefore, the integral of cotangent squared of x with respect to x is going to be equal to the negative cotangent of x minus x plus c. The next two integrals we are going to solve are my personal favorite out of these bunch, and they are the integrals of the sine cubed of x and the cosine cubed of x. In order to solve these, however, we are going to need the values of the sine of 3x and cosine of 3x. Why? Because they make finding the sine cubed of x and cosine cubed of x as integrals easier. I actually solved these in a separate video. If you want to look at that, click this video in the top right here. Carrying on though, the sine of 3x is equal to 3 times the sine of x minus 4 times the sine cubed of x. Similarly, the cosine of 3x, which I'll write over here, the cosine of 3x is equal to 4 times the cosine cubed of x minus 3 times the cosine of x. Using these two, we can get the sine cubed of x and cosine cubed of x in terms of simpler values that we can easily integrate. Starting off, in order to get sine cubed of x on its own here, we need to divide everything by negative 4. Doing so, first let's take this to this side and divide everything by negative 4. So then doing so, we get the sin³ of x being equal to, this thing on the right side will become -3 sin of x. So here -3 sin x plus the sin of 3x divided by -4, which you can rewrite as being equal to 3 times the sin of x minus the sin of 3x all divided by 4. This identity here is the one we are going to be using in order to find the integral of the sin³ of x more easily. As for this expression for the cosine³ of x, we are going to be using this one in order to find the cosine³ of x nicely. Here it's actually simpler to do. We can take this to this side, giving us 3 cosine of x plus the cosine of 3x, and then dividing by 4, we get that the cosine³ of x is equal to 3 cosine of x plus the cosine of 3x all divided by 4. This identity is what we're going to be using in order to easily find the cosine³ of x's integral. So then, let's use these two identities in order to find the integrals of the sin³ of x and cosine³ of x. Starting off, the integral of the sin³ of x with respect to x is going to be equal to the integral of the other expression which is equal to it. The other expression which is equal to it is the expression 3 sin x minus sin of 3x divided by 4. Copying that down, we can see that we have the integral of 3 sin x minus sin of 3x divided by 4. Considering the first bit, we can take this 3 and this divide by 4 out and say that this first part is 3/4 of the integral of the sin of x with respect to x. And then taking the second part of the integral, it is -1/4 times the sin of 3x's integral, which is -1/4 times the integral of the sin of 3x dx. Now then, on the first bit, we have 3/4 of the integral of the sin of x. The integral of the sin of x is the negative cosine of x. So therefore we can substitute in there the negative cosine of x. As for this bit, we leave the -1/4 as is, and the sin of 3x's integral, as we know from our formula, since we have a constant of 3 multiplied by x here, its value is going to be the negative cosine of 3x divided by the constant of 3, and then plus c. Simplifying this all out, we can see that this negative and this negative will cancel, and we have a cosine of 3x in here. Simplifying the terms, this thing, this negative and this 3/4 will be written as -3/4 times the cosine of x. As for this bit, I'll be writing this -1/4 and this -1/3 as positive 1/12 of the cosine of 3x. So I'm going to write cosine of 3x plus c. Now we could end it here. However, since we know the identity of the cosine of 3x, we can actually simplify this further. We know that the cosine of 3x is equal to this expression here. Copying this down, we can write instead of the cosine of 3x, the value of this thing right here. So here what we need to do is to leave this -3/4 of cosine of x alone. So here we have a -3/4 cosine of x plus 1/12 of this whole expression here plus c. Now then, simplifying this down, we have the -3/4 of the cosine of x. For this bit, this 1/12 times 4 times the cosine³ of x is going to cut the 4, leaving us with 1/3 of a cosine³ of x. So we're going to write that down as cosine³ of x divided by 3. As for the second bit, the -3 cosine of x divided by 12 is going to cut the 3 in the 12 for this 3, leaving us with 1/4 of negative cosine of x, which I'm going to write as -1/4 cosine of x plus c. We can see that this 3/4 cosine of x and this 1/4 cosine of x will add together to give us a whole -4/4 of a cosine of x, as in just negative cosine of x. This thing we're going to leave as is, as cosine³ of x divided by 3 plus c. Therefore, finally, we can say that the integral of the sin³ of x with respect to x is going to be equal to the negative cosine of x plus the cosine³ of x divided by 3 plus c. Similarly, we can do the same exact thing for the integral of the cosine³ of x with respect to x. We can replace the cosine³ of x with the expression that we had above and integrate as normal. Doing such, we can see that the integral that we need to find is the integral of this expression here. Copying the expression down and pasting it into that gap, we can see that what we need to find is the integral of 3 times the cosine of x plus the cosine of 3x divided by 4. We can break this into two integrals, of course. Doing so, the first integral, we're going to take the constant of 3/4 out and say this is 3/4 times the integral of cosine of x with respect to x, so times the integral of cos² dx. For the second bit, this is cosine of 3x divided by 4, which I'm going to take the 1/4 out and say this is plus 1/4 of the integral of the cosine of 3x with respect to x. Now then, the integral of the cosine of x is the sine of x, so we can write this part as simply 3/4 of the sine of x. As for the second bit is 1/4 of the integral of the cosine of 3x. We know that when we have a constant times the thing on the inside, all we have to do is take the integral normally and substitute the 3x on the inside and then divide by that constant, which is 3. So therefore what we have here is the integral of the cosine of 3x being equal to the sine of that same value, which is 3x, divided by the constant of 3 and then plus c. Now we're not going to leave it like this, we're actually going to substitute in the sine of 3x and simplify this into a nicer value. We're going to rewrite it first. We're going to rewrite the sine of 3 divided by 4 times the sine of x plus this 1/4 and this 1/3 I'm going to turn into 1/12, so plus 1/12 of the sine of 3x plus c. For the sine of 3x, we're going to be substituting this expression that we had up here. We had that the sine of 3x is equal to this bit over here, 3 times the sine of x plus, actually minus 4 times the sine cube of x. Substituting that into this expression here, we can see that what we have is equal to 3/4 of the sine of x plus 1/12 of this expression here plus c. Now then, evaluating this bit, 3 sine of x divided by 12 is going to give us this thing cancelling with this thing and 1/4 sine of x. We can write that down as being 3/4 sine of x plus the 1/4 sine of x, and then this negative 4 sine cubed of x is going to cancel with this 1/12, leaving us with negative 1/3 sine of 3x, which we're going to write as negative sine of 3x divided by 3 and plus c. This 3/4 of sine x and this 1/4 of sine x I'm going to concatenate into a single 4/4 of sine of x, as in just sine of x. And then this bit I'm going to write as negative sine of 3x divided by 3 plus c. Therefore, the integral of the cosine cubed of x with respect to x is going to be equal to the sine of x minus the sine of 3x divided by 3 plus c. To wrap up this lesson, we're going to consider one more rule of integration, and that is something called integration by parts. Integration by parts is actually derived from the product rule. Recall the product rule that states that if you have the product of two functions, let's say the derivative of f of x times g of x, as in you have a product of two functions and you take the derivative, this is going to be equal to the derivative of the first function, so f prime x, times the second function g of x, plus the second function derivative, so g prime x, times the first function f of x. From this we can see, since we have derivative on one side equal to another function on the right side, we can see from this that if we take the integration of this thing, we can see that f of x times g of x would in fact be the integral of f prime x times gx plus g prime x times fx with respect to x, as in if we have one function derivative times another function plus the second function derivative times the first function, that integral is going to give us the first function times the second function. However, for integration by parts, this is not the format that we put it. Instead, what we do is break this integral into two pieces. So what we're going to do is break the integral into two pieces, giving us that f of x times g of x is equal to the integral of f prime x times gx with respect to x plus the integral of g prime x times fx with respect to x. Then what we do in integration by parts is to take one of these integrals to the other side by subtracting it. Doing so, we can get something of the form f of x times g prime x with respect to x being equal to f of x times g of x minus the other integral, which is going to be the integral of f prime x times gx with respect to x. You can see for the first part we have the f on its own and g prime. On the second integral we have f prime and g on its own. So then we have this expression here. This says that if we have one function multiplied by another function's derivative and we integrate it, the resulting function that we get is going to be the original first function times the integral of the second function, as in this, if we treat this as its own function, its integral is going to be here minus the integral of the first function's derivative times the second function's integral, as in we have a way to find the integral of a product of two functions like this. Usually, however, this is not presented in this form. We don't write the integral of f of x times g prime x and so on. Usually in normal schools you will see this being represented as u times v prime's integral being equal to u times v minus the integral of u prime v dx. This is the exact same thing. However, in the interest of being nice and concise, we've abbreviated f of x as being a function u and g prime x as being a function v prime. And such, we have now written that the integral of u times v prime with respect to x is equal to uv minus the integral of u prime times v. Sometimes you'll also see that we've written this without the dx. I personally don't like this, but since the variable that we're integrating with respect to is kind of implied in the function itself, we don't even need to write the dx bit. We can simply write that the integral of u times v prime is equal to uv minus the integral of u prime v. I often see people writing it like this. This is integration by parts. It is a way to turn a product of two functions into a different expression of products of different functions and integrals. Here we can see, if we have a product of two functions and we integrate it, where one function is u and the other function is some other function v's derivative. In that case, the integral of u times v prime is equal to u times v minus the integral of u prime times v. Let's now look at an example of this and see how we can use integration by parts to solve our problems. To do this, let's take the example integral as the integral of x squared times the sine of 2x with respect to x. And let's suppose that we want to solve this integration using integration by parts, as in we want to consider one of these functions as u, one of these functions as v prime, and then see if we can simplify this thing into a separate form of expression. In this case, since there is a complete ambiguity in which function is u and which function is v prime, we actually get to choose for ourselves which of these two functions we choose to be u and which of these two functions we choose to be v prime. Ideally, since v prime needs to be integrated to get v, we want the easier function to integrate to be v prime and the more difficult function to integrate to be u. In this case, however, it is somewhat simple to do both integrations of x squared and sine of 2x, but since x squared is going to get smaller but sine of 2x is not going to get smaller when we take the derivative, we're going to take u as being x squared, since u prime is going to be simpler, and if we do it again, we're going to see we get even simpler results. So in this case, we're going to take the function that we take the derivative of, as in the function u, to be x squared, in which case the other function is going to be sine of 2x. So we're going to say let u equal x squared and v prime equal the sine of 2x. Given this, we need to find u prime and v. U prime is easy to find since u prime is simply the derivative of x squared with respect to x, which is going to be just 2x. As for v prime's integral is going to be v. V is going to be this thing's integral. We already know how to find the integral of something like this. The integral of sine of x is the negative cosine of x. Therefore, if we have the integral of the sine of 2x, it's going to be equal to the negative cosine of 2x divided by 2. Now we have our values of u, u prime, v and v prime. All we have to do now is, according to this formula, substitute our values and find the value of this integral here. To do this, I'm going to call this integral I. So we're going to say I equals this thing. We're going to go down here and say that according to our formula from up here, all we need to do is write u times v minus this integral here. U is x squared, so we write x squared multiplied by v, which is the negative cosine of 2x divided by 2. So multiplied by negative cosine 2x divided by 2 minus the integral of u prime times v. In this case, u prime is this function here, which is 2x multiplied by v, which is going to be the negative cosine of 2x divided by 2. So multiplied by the negative cosine of 2x divided by 2 integrated with respect to x. So now we have changed our integral I into a different form. Simplifying this thing, we can see from this first term we can take the negative out, so we can have negative x squared times the cosine of 2x divided by 2. As for this second bit, we can see that this negative could be cancelled with this negative. Cancelling it out, we get plus the integral of 2x times the cosine of 2x divided by 2. This 2 and 2 can be cut to give us just x times the cosine of 2x's integral. So what we have here is x times the cosine of 2x's integral. Now, this actually allows me to bring up another interesting property of integration by parts. Usually, when you're doing integration by parts on certain functions, you will be required to do integration by parts multiple times. As in, you do integration by parts providing you with one function and another integral, as in, you do integration by parts on this integral to give you one function and another integral, and oftentimes this integral will require you to do integration by parts once again. So then, in this case, we actually have one of those integrals. The integral of x times the cosine of 2x dx requires us to do integration by parts again to get a nice answer. In order to do this, we are going to call this integral j and take it aside, solve it separately and bring it back. So we're going to go down here and consider j. J is the integral of x times the cosine of 2x with respect to x. We are going to be using the same operation of integration by parts on this integral here. Recall, the integration by parts says that if we have a function u times the function's derivative, which is v prime, it is going to be equal to u times v minus the integral of u prime, as in the derivative of u, times the original function of v, and this thing can apply for any valid functions u and v. So then all we have to do is choose the functions u and v from this thing and simplify with this expression here. For this thing, I'm going to choose this to be u and this to be v prime. The reason is that x is going to simplify into a constant when we take its derivative, as in this u prime is going to be a constant. Doing so, let's say let u equal to x and v prime equal to the cosine of 2x. Now I need to find the value of u prime and the value of v. Here the value of u prime is simple, it's simply 1 because the derivative of x with respect to x is simply 1. As for v prime, when we integrate v prime, we have to take the integral of the cosine of 2x. The integral of cosine of x is sine of x, therefore the integral of cosine of 2x is going to be equal to the sine of 2x divided by 2. Now all we need to do is use the integration by parts formula and substitute these values in here. So we have uv, u is x and v is this expression here. Substituting those two in, we have x times the sine of 2x all divided by 2, and then minus the integral of u prime times v. U prime is 1, so we have 1 here, times v, which is the sine of 2x divided by 2. So here we have sine of 2x divided by 2 dx. Now then, this first term here is already simplified. All I need to do is simplify this thing. Luckily for me, this is where my integration by parts ends, because this thing can actually be solved directly. So here we have j equal to x times the sine of 2x divided by 2, and I'm actually going to take this divide by 2 outward as a minus 1/2 times the integral of the sine of 2x with respect to x. We know how to solve the integral of the sine of 2x. It is simply the negative cosine of 2x divided by 2. Therefore, j is equal to x times the sine of 2x divided by 2 minus 1/2 times the integral of the sine of 2x, which is going to be equal to the negative cosine of 2x divided by 2 plus c. Now then, simplifying this thing, we can see that this divided by 2 and this divided by 2 could come together to get us a divide by 4, and this negative could cancel out, leaving us with x times the sine of x, sine of 2x, divided by 2, plus the cosine of 2x divided by 4 plus c. Now what we need to do in order to evaluate the original integral I is substitute the value of j that we found into here. So therefore I'm going to rewrite this I expression and then substitute in j. Rewriting I is equal to the negative x squared times the cosine of 2x divided by 2 plus the value of j, which we can now substitute as being equal to negative x squared times the cosine of 2x divided by 2 plus this whole expression here, which is going to be x times the sine of 2x divided by 2 plus the cosine of 2x divided by 4 plus c. Now you can simplify this however you want. You can group the cosine of 2x terms together or whatever, but this is the simplest expression for the integral I. So now we can see how we can use integration by parts in order to find the integrals of certain functions more easily. Here, rewriting this as a final answer, the integral of x squared times the sine of 2x, which I'm going to rewrite down here, the integral of x squared times the sine of 2x with respect to x is equal to this whole expression here, found using integration by parts. So that is actually going to be the end of this video here. In the next video, we are going to be going over some more identities with integration and something called finding the volume of revolution of a certain graph. So then, that's going to be all for this video. Thank you for watching and goodbye.